This is part 2 of module number 5, Forecasting Methods, of STAT 560, Applied Business Research and Statistics. In the previous methods we discussed, we took averages going back one period for the naive forecast, all the periods to the simple forecast, or a select number of periods for the moving average forecast. However, we're not providing different weights for information obtained at different times. And this is done through the exponential smoothing. It defines the forecast for the following period as the actual observation from the prior period, AT, multiplied by a constant, which varies between 0 and 1. We will talk about that one in a second. Then it adds the actual for two periods before, T minus 1, and multiplies that number by alpha times 1 minus alpha. Then it adds the actual for three periods before, but multiplies that number by alpha 1 minus alpha to the square. And then goes through the third, the fourth, all the way to T minus 1 and T. So these coefficients that multiply demand decrease exponentially. And we can see that in this chart. So for example, if we start with alpha equals 0.6, and that multiplies the demand for the prior period. When we multiply the demand for two periods before, we use a number that ranges between 0.2 and 0.3, and then that number continues to decline exponentially, and that's the reason we call this exponential smoothing. If we start with alpha 0.5, the decline continues. It's a bit slower than it is for large alphas, but eventually the numbers will continue to decrease. And that happens with 0.4, etc., etc. That's why we call this exponential smoothing. By rewriting this same math that is here, the forecast for the future period, for the next period, equals the forecast for the current period plus alpha multiplied by the difference between the actual for the current period minus the forecast for the current period. And this is the formula that we just saw before, written in a much more simplified way, and we will use this formula as we calculate forecasts in the next tutorial. Professor Holt in the late 50s extended the concept of exponential smoothing by adding another element to consider trend. Under this forecasting method, we take into account the level as well as changes in trend. The two expressions now that build the forecast are the level element, which takes into consideration alpha in a very similar way to the single exponential smoothing method. But it also adds the element of trend, which is given by including a beta factor. Adding the two together will give us the forecast that includes level as well as trend. We will use that methodology in the next tutorial. This chart shows a comparison between the simple exponential smoothing method and the Holt exponential smoothing method, or double exponential smoothing method, as we just described. We can see the difference here when we look at the error measures. So the mean absolute error when we use the simple exponential smoothing method is 66.18 versus 58.30 that we obtain by using the double linear exponential smoothing method. We see an improvement also in the mean square error as expected, also represented in the mean absolute percentage error, or MAAP. The change in the forecast is not that significant. It goes up from 564 bags to 568 bags. A few years later, one of the students of Professor Holt suggested the addition of a third component to the doubled exponential smoothing method to consider seasonality variations, thus creating what we call now as the Holtz-Winters methodology that takes into account level, trend, and seasonality, and incorporates a third factor known as gamma, which is also an arbitrarily selected factor between 0 and 1, similar to alpha and beta. As you will see in the tutorial, applying the methodology using stat tools will give us this result. This chart shows a comparison between the double and triple exponential smoothing methods, in this case applied to the Beer problem. And the reason we have chosen the Beer problem is because we have a longer database And in order to apply the Holt-Winters method, we need more data points than we had in the diaper problem. We can see that the triple exponential smoothing method takes a closer look at seasonality and in fact projects seasonality quite reliably here. This is also reflected in the metrics. The mean absolute error goes down from 59.01 to 26.05, and we can see improvement in the other metrics as well as expected. The change in the forecast for the upcoming period, in this case period 25, is also reduced considering the seasonality element. Check the tutorial to learn how to create those charts using stat tools.